Good morning, all of you, my dear students. Today we are going to discuss about mechanical properties of fluids, session 5. And that mainly you can discuss pressure energy and force of buoyancy. After force of buoyancy, we can go for Archimedes principle. So today the first topic is that the session 5 is part of that pressure energy. Pressure energy. Are you able to see the screen? Pressure energy heading.
Yes, sir.
Right. Now we know already in mechanics we have studied about kinetic energy, we studied about potential energy, and total kinetic energy and potential energy we called as mechanical energy also. And other than this, we know that heat energy, light energy, sound energy. There are different forms of energy, we know that. So, similarly, in the case of fluids, now there is important energy which is called as pressure energy. Pressure energy. Okay, what is pressure energy? The energy possessed by a fluid, the energy possessed by a fluid by virtue of its pressure, by virtue of its pressure is called its pressure energy. Okay, so we can called as the energy possessed by a fluid, the energy possessed by a fluid or a liquid by virtue of its pressure, by virtue of its pressure is called pressure energy, is called its a pressure energy. Okay, pressure energy. Are you clear this point? The energy possessed by a fluid by virtue of its pressure is called its a pressure energy. So how to understand this pressure energy, where we can see in real life? For example, I have seen the water dam. There are different dams will be constructed on the rivers. So we can see the water dam. So all of a sudden, if you open the gates, how much pressure you can absorb, how much pressure, with the high pressure, the water will come out or spill out. Okay, so that means whenever you can observe the big water dams, in that we can observe this pressure energy. These are the real time examples we can see. Okay, so how to calculate this pressure energy? What is that value? You can see. For that, you can take a simple container. So instead of a big dam, a simple container you can take like this. Okay, that container connected with a pipe at the bottom part of the container. There is a pipe like this. Okay, now you can see. So let us say it contains certain amount of water. This is the free end of the surface of the container. Here it has, there is some liquid level or fluid level. Okay, so this pipe or a tube connected to this. Let us say this tube connected to this. So this side you can put one piston or a, we can say some tap. Let us say piston we are putting here instead of tap. There is a piston P. There is a piston at the bottom. Okay. Now here, let us say the density of this liquid is rho, and the height of the liquid, this height of the liquid at the center of this up to center of this tube is h. Okay, for the reference, for the, okay, and at this point up to this point, let us say the pressure at this point is, let us say P pressure. Rho is the density of the liquid. Okay, T is the tube, this tube connection. Okay, let us say small a be the area of cross section, area of cross section of this tube, area, small a. Okay, because of small tube, let us say small a. Okay. Now, outside pressure, we know already atmospheric pressure will be there, P naught. Okay. If it is open, if it is closed, then that is a different. Open only if you can take. So after this, are you clear? Now, this side also atmospheric pressure you can expect. This also open only. No? If the piston is open, this side also atmospheric pressure will exert. So both sides atmospheric pressure will exert whenever this tap is open or this piston is open. Okay, right. After this, are you clear? So this is about a tank of water you can take in, and it has certain height h. There is a tube or opener connected at the bottom end that is connected with the tube. The area of cross section of the tube is small a. The pressure at the center of this tube at this point is P. What is this pressure value normally? Pressure due to this liquid. P is equal to only due to liquid is P is equal to H rho Z. Okay, along with atmospheric pressure, then P is equal to P naught plus H rho Z. Okay, are you clear this point? Suppose if we can add atmospheric pressure also, P is equal to P naught plus H rho Z. Okay, right. Now, suppose this piston, we want to calculate the pressure energy here mainly. Okay, so that means we need to do certain work, then that work will be stored as its energy. Suppose this piston has to move slowly. First of all, before going to move the piston, how much force acting on the piston we need to calculate. How much force acting? Already said at the piston point of view, at the center of the small tube, what is the pressure value? P. Then force acting at that point on the piston, force acting on the piston by the fluid due to its pressure. F is equal to P, pressure into area of cross section of the piston or a tube, P into small a. Small a is the area of cross section of the tube. So this much force is acting or acted by the fluid on the piston. Okay, are you clear this point? This much force acting on the piston by the fluid because of its pressure. F is equal to P into small a. Now what we need to calculate the work done. That means work done will be stored as its pressure energy in this case. So that same amount of force I can take F, PA force on the piston, then same amount of force you can apply inward direction. And by applying this inward direction, this piston has to displace by displacement x inwards. Okay, so that by using the same amount of force, if by applying externally, and this piston is pressed inwards by a distance x, then there is a height of the liquid slowly increases because of this volume is going inside now. Then how much volume is going inside? Volume change or volume going inside is volume is equal to this x distance into area of cross section, that is equal to V. Therefore, V is equal to x into A. This much volume is going inside. Okay, because of this volume, the pressure energy is stored in this volume of the fluid. Now work done by this applied force F is calculate. Work done is equal to, and that piston has to displace slowly only. Why? Because slowly, because we are not considering any kinetic energy. If you do very fastly, then it will go into convert into kinetic energy of the fluid also. But we are doing only that pressure energy. So that work done is equal to product of force into displacement. So force F into x. Okay, see force acting from right to left, the displacement also from right to left. Then there is no difference. So F into x. What is F value? P into A x. So that work done is PAX. PAX. Okay. So what is this A into x? We know already. A into x, what is this? V. Then that we can write as P into V, where V is the volume going inside. Okay. So this P into V is the pressure into volume. will be stored as its a pressure energy. This work done by the applied force stored as its a pressure energy. Therefore, the pressure energy is equal to, therefore the pressure energy is equal to P into V, P into V, where V is equal to X into A, P is the pressure at this point. Are you clear this? The pressure energy value? Are you able to following? Right.
Yes.
So that means the pressure energy stored in the form of whatever V amount of volume of the liquid raised, in that volume it is storing. Okay, that is the point. Suppose above a certain level, let us say red dots, this level where the liquid rises, there the pressure energy will be stored. That is equal to P into V. Okay. So now there are certain small applications on this pressure energy. Pressure energy per unit volume, what you can say. Pressure energy per unit volume. That is equal to PV by V. VV cancel. That is equal to again P. That means static pressure. Static pressure. So the pressure energy per unit volume we can call it as static pressure. Next, pressure energy per unit mass. Pressure energy per unit mass. That is equal to PV by M. Okay. We know already density rho of the liquid is M by V. Okay, then M is equal to, you can write rho into V. Then you can write PV by rho into V. Then VV cancel. That is equal to P by rho. This is pressure energy per unit mass, P by rho. Next, this is, there is no specific name. Before pressure energy per unit volume is static pressure. Here pressure energy per unit mass. Next, pressure energy per unit weight. Pressure energy per unit weight. That is equal to PV by mg. Instead of per m mass, now mg weight. Okay. Then you can write PV by m means we know already rho v into g. Then this VV cancel. So that P by rho g. P by rho g. This P by rho g or pressure energy per unit weight is called pressure head. The name of this one you can call it as pressure head. Pressure head value. In fluid dynamics, in future if you go for engineering, directly they will give the pressure head value. Okay, the pressure energy per unit weight of the liquid you can call it as pressure head. That is equal to P by rho g. So that we studied here a small application points, pressure energy per unit volume, that is equal to static pressure PV by V, that is equal to P. Pressure energy per unit mass P by rho. Pressure energy per unit weight P by rho g. Are you clear this all the points? So this is about understanding about pressure energy. Okay. Understood now?
Yes, sir.
Next we'll go for force of buoyancy or buoyant force. Force of buoyancy or buoyant force. Force of buoyancy. Force of buoyancy. That is also represented with the symbol F suffix B. FB, F suffix B. Force of buoyancy. Okay, where we can feel this force of buoyancy. What is this force of buoyancy? Suppose if you can see, suppose you have an object or a bucket. You can keep this bucket of water or this object or solid object, keep inside the water. Have you observed any time? You can play so many times at your childhood. You can keep an object whether fully filled with water or simply empty object or some solid object. Whatever object you can take, you can keep inside the water. What happens? What you observed here? The weight of the object is slightly decreased. Have you observed any time? Whenever you can keep the object inside the water, the weight of the object is slightly decreased. Yes or no? Yes, the
Yes,
weight of
sir.
the object is slightly decreased. That means what? There is a weight loss. There is a weight loss whenever it is inside the liquid or fluid. Or else we can say the total weight at that situation we can call it as the apparent weight. The total weight we can call it as the apparent weight. So that means you have a fully filled bucket of water. Inside the water you can keep. It is something like you can feel weightless. Whenever it is lifted upside from the water, then immediately you can feel there is a full weight. Okay, that difference you know. So now you can see the force of buoyancy is there is a resultant upward force acting on an object. Okay, due to fluid pressure difference or a liquid pressure difference. We know already liquid pressure will be increases from the top surfaces to bottom surface. Suppose let us draw the diagram, we can for a clear understanding. You can take again a tumbler or a container of water. In that I'll explain. In that you can keep one solid object so that you can understand very clearly. Now you can take a solid object like a cylindrical solid object. This is a solid object. So a solid object you can take. This is not an imaginary column of liquid. This is a solid object. This is an object. Keep in mind. This object has, let us say, mass m. Let us say mass m. This density of the object, let us say some sigma. Okay. Now, here, surrounded by this object, there is a fluid or liquid. Okay. So this is the fluid level or liquid level in the red dots are dotted. Red dots is the liquid I have taken. Blue is the object. Now, this object is fully immersed. Let us imagine. So this face area you can take, we know already, capital A. So let us say this is the point P, this is point Q. This is the topmost face, point P, bottommost face, point Q. From the free surface of the liquid, from the container. So from the free surface, the height of the first face is H1. That means the depth. It is at a depth of H1 level. The bottom surface is depth of H2 level. Bottom surface is at a depth of H2 level. Top surface at a depth of H1 level, bottom face at a depth of H2. Okay, that means what you can understood, the pressure at the bottom surface is more than that of pressure at the top surface. We know already. Okay, that means what, there is a resultant pressure difference. That pressure difference will make there is a net force acting. That net force acting upward direction. Okay, so normally upward fluid acting vertical direction. Okay, and the downward fluid vertically upward. Then resultant force, you can see here, resultant force will act vertically upward direction. That resultant force you can take like this. Like this, there is a resultant force acting on the body vertically upward direction. So that resultant force acting vertically upward direction, you can call it as the FB. FB. What is this FB value? You can calculate. Okay. So I can define once again. FB is the buoyancy force. It is the resultant force acting on your body by the liquid when it is partly or fully immersed in liquid, and the resultant force acting vertically upwards and perpendicular to the surface of the liquid. Are you clear this point? Right. Okay, Sundar, please share your YouTube channel link. Please, sir, I can't find the particular channel. Please share. Yes, the channel link, let us. Samba space Siva Meduri. Okay. Sundar Sambasiva Medore. This is the channel. Okay, thank you. Right. Now you can see here, what is force of buoyancy? I said there is a buoyant force is defined as the resultant force due to fluid pressure. The resultant force due to fluid pressure acting vertically upward direction. Okay, when an object is immersed inside a fluid. When an object is immersed inside a fluid, there is a resultant force acting vertically upward direction due to fluid pressure difference from the top surface to bottom surface. Okay. Now you can see this FB value for that net force. See, we know already at the point P, there is a upward liquid will give a force F1 in the downward direction. Okay, there is a force F1 here. Here force F1 acting vertically downward direction. Here force F2 acting vertically upward direction. Okay, so we need to calculate F2 minus F1. What is F1 value? So outside we have atmospheric pressure, we know that already. So this F1 value you can calculate. First pressure value you can calculate. Pressure at point P. Pressure at point P we know already, P1. Yes or no? Pressure at point P is P1. P1 is equal to P0 plus H1 rho G. Are you clear? P1 is equal to P0 plus H1 rho G. Then force at point P. Force at point P. F1. F1 is equal to P1 into A. Let us say A is the area of cross section. Okay. Then what is this F1 value? F1 is equal to P0 plus H1 rho G into A. This is F1 value. Let us say the cylinder height, object height H you can take. And the density sigma. And the density of the fluid is, let us say, rho. Okay. Then F1 is equal to P0 plus H1 rho Ga. This is equation number 1. Similarly, pressure at point Q, at the bottommost point. Pressure at point Q. P2 is equal to P0 plus H2 rho G. It is equal to P0 plus H2 rho G. Then force at point Q. Force at Q is equal to F2. F2 is equal to P2 into area of cross section. That is P0 plus H2 rho G into A. Then net force FB. Okay, net upward force. Net force you can call it as FB. That is upward force. That is F2 minus F1. F2 minus F1. F2 value P0 plus H2 rho G into A. So you can do A also can multiply. P0 A plus H2 rho G A minus P0 A plus H1 rho G A. Are you clear this equation? Net force, net upward force FB is equal to F2 minus F1. That is P0 A plus H2 rho G A minus P0 A plus H1 rho G A. P0 A cancel. Then you can write H2 rho G A minus H1 rho G A. Rho G A is common. Rho G A into H2 minus H1. Height difference. What is H2 minus H1? H from the diagram. H2 minus H1 is equal to H. Then you can write buoyancy force FB is equal to rho Ga into H. Rho Ga into H. Are you clear this equation?
Yes, sir.
Right. So then A into H, what you can write? Area of the cylinder and height of the cylinder. Then you can write V. Volume of the cylinder is equal to area of cross section into height. Then you can write this value rho G V. Rho G V. Okay. Or rho into V into G. Rho into V into G. Where V is the volume of the cylinder. Rho is the, rho you can see here. Rho is the density of the fluid. Keep in mind. Volume of the cylinder into density of the fluid. Okay, where sigma is the, I said, density of the cylinder. Then you can multiply sigma for this, divide sigma, suppose. Multiply sigma, divide sigma. Then you can write sigma V, rho by sigma into sigma V, rho by sigma into sigma density of the solid multiplied and divided. So that rho by sigma into sigma Vg, sigma Vg. So let us say m is the mass of the cylinder, I said, then m mass is equal to what you can write, sigma into volume. Density sigma into volume. Then sigma into volume, what you can write, mass of the cylinder. Then P, this rho by sigma into mg. Rho by sigma into mg. Okay. Then you can write FB, balance force, is equal to mg into mg into mg into mg weight of the solid cylinder into rho by sigma. Are you clear this? Mg into rho by sigma. So what is this? Balance force, net upward force. Net upward force is equal to loss in weight of the body. Loss in weight of the body. Are you agree this? When it is immersed in the fluid. Loss in weight of the body. So then what is the apparent weight? Okay, suppose initially 50 kg. Okay, 50 kg weight. Then if it is inside, we can feeling that loss in weight is 20 kg. Then apparent weight is 30 kg. Then apparent weight, how to calculate? Apparent weight of the body. Apparent weight of the body is equal to actual weight minus loss in weight, loss of weight due to immersion fluid. Apparent weight of the body is equal to actual weight minus loss of weight. So then actual weight mg. Yes or no? M is the mass, then mg is the actual weight minus loss in weight, how much? Mg rho by sigma. Yes or no? That FB means what I said, loss in weight of the body. Okay, net upward force, na? Net upward force will make that loss in weight of the body. So that mg rho by sigma. Okay, where rho is the density of the fluid, sigma is the density of the solid. Rho what? Density of liquid or fluid. Rho. Okay, where sigma is density of solid body. Keep in mind. Density of solid cylinder body. Okay, then you can write mg. The apparent weight of the body is Puja mg into 1 minus rho by sigma. The apparent weight of the body is mg common 1 minus rho by sigma. Mg into 1 minus rho by sigma. This is the apparent weight. Apparent weight of the body. Whenever it is inside the liquid. Are you clear up to this? Hey. So I recall once, force of balance FB is the net upward force acting on the body due to fluid on the solid body because of the pressure difference. And this we have calculated as by using pressure difference force. That FB, F1 upward direction, you can say upside, F2 bottom side, and F2 minus F1 resultant force, that is equal to H2 rho Ga minus H1 rho Ga, and that H2 minus H1 difference is height of the cylinder H. From that we have calculated that FB is equal to rho Gv at certain point, rho Gv. Rho G means actually what? Rho into V. Rho is the density of the fluid, rho into V. That means this is equal to amount of the weight of the fluid, equal amount of weight of the fluid that is inside the solid, that is equal to balance force. Okay, and that is equal to loss in weight of the body, that is equal to loss in weight of the body. Okay, then whenever weight is lost, then there is a apparent weight. Instead of actual weight, we can calculate apparent weight. Apparent weight means actual weight minus loss of weight. So actual weight is how much? Normally, if it is outside, m is the mass of the cylinder, then actual weight is mg. Then loss in weight is fb. Fb how much? Mg into rho by sigma, where rho is the density of the liquid, sigma is the density of the solid. Then mg rho by sigma. Okay. Then you can write apparent weight is equal to mg into 1 minus rho by sigma. Are you clear this? Right. Now, what are the factors that force of buoyancy Fb depends on? We can see here. So, force of buoyancy acting on a body is numerically equal to weight of the fluid displaced. Actually, this force of the buoyancy is equal to weight of the fluid displaced. Weight of the fluid displaced by the body. Force of buoyancy exactly equal to weight of the fluid displaced by the body. Okay, this in this way also you can write weight of the fluid displaced by the body. Okay, so this will be true whether the object is partially immersed or fully immersed. It will be true. It will be true whether the object is completely immersed or partially immersed. Is it true for object? Object is floating. That means floating means partially immersed. Object is floating or completely immersed. Or immersed in the body. Immersed in the liquid. Okay. So this is about one more point regarding Fb. That is the force of buoyancy is equal to weight of the fluid displaced by the body. Okay. Whether the
Sir,
body. Yes. Tell me.
sir, please scroll the page up, sir. I want to take notes, sir.
Yes.
Sir, no, sir. Little down, sir.
Yes.
Ah, yes, sir. Yes, sir. Sir, so that previous step, sir. Ah, yes, sir.
Okay. Right. So this is about Fb. Next, this force of buoyancy independent of mass and size and density of the body. So here, force of buoyancy, you can see here, what is the value? Exactly, you can say a rho weight of the liquid into V, volume of the liquid into G. Okay. So it is independent of the mass and size and density of the body. And it depends on the volume of the body inside the fluid. Depends on volume of the body inside the fluid. How much volume is inside the fluid, that is important. The force of buoyancy depends on volume of the body inside the fluid. Okay. And depends on nature of fluid. Nature means density. Depends on nature of fluid. Nature of fluid means density, fluid density. Okay. Density of fluid. And it depends on acceleration due to gravity also. It depends on acceleration due to gravity at that point. Depends on G value, acceleration due to gravity. Okay. So that's it for the day. So time up.